Good afternoon, ladies and gentlemen. My name is Chiravachradej. Today we meet again to talk about a new topic on stress, and this time we will include deformation as well. This time we look at the axial forces effect, the effect of axial forces, bending moment, and the shear forces. Okay, the axial forces we look at the stresses and the deformation, whereas the bending moment and the shear we look at only stresses. For the torsion, again we look at two components, both the stresses and deformation. The deformation of the bending moment we'll discuss a bit later in the second half, but for now let's move on with this topic for today, the torsion. Okay, we again discuss about what we need to know before we start on learning this topic. Then we look at the physical phenomenon on how the behavior is. Then from that information we'll start to form the equation, or we formulate how we calculate all these physical phenomenon. And before we go on, because we haven't done much about the polar area moment of inertia, I will actually present one calculation for a circle for the polar area moment of inertia. Why we need it, we will see it a little bit later on. And then once we find that, we know how to find the polar area moment of inertia, then we'll see the examples of the stress and deformation caused by torsion. The background we need is the ability to calculate, of course, the torsion itself at any given point on a structure. The understanding of the general concept of the shear stress, and the understanding of area moment of inertia, because it will relate in some sense, as I indicated already, that we will need to use the polar area moment of inertia. Now let's look at the physical phenomenon. Okay. Again, I will use the rubber to demonstrate the change of the material or the deformation of material once it is subject to the pure torsion. This is the same rubber we have been using all the way through, that is the rubber with the two lines across the height of the beam per se. So if we put the torsion into it, or in fact twisting it, okay, notice the two lines. The two lines is actually did not change the angle between them. Okay, it still keep on looking parallel. Okay, the change is in fact on the cross section area, not on the front view. This one is a front view. So if we look at the cross section area instead, then we could see better how it deformed. Now if we turn, as I said, look at the cross section area, there we are. If that represents, there's another line I draw on the cross. This one is represent the cross section area. When I twist it, notice when I twist it this way, then on the cross section area will be twisted this way. Notice the line, that's the movement of the line, and this time is a straight line. You see it as a horizontal line, correct? Now when I actually put a torsion into it, twist it per se, then that line doesn't change any, it still remains straight line, what I meant, or as straight as it was before. However, what happened is it's rotate around. Okay, and if you notice the rotation, this line here, I actually draw it through about the centroid of the area. Notice when it rotates, when the cross section area rotates, it rotates around with the center at the centroid of this area. Well, this is symmetry. Okay, this is for let me rephrase this. If it's on a symmetry area, if the cross section area is a symmetry area, then when you rotate it, when you twist it, that line will rotate, the cross section will rotate with the center at the centroid. Okay, it remains a straight line though. Now because we are not using the rubber anymore, I like you to focus a little bit on my hands. Okay, notice that, back to rubber a little bit. Notice the rubber, when I twist it, okay, these two lines similar to when we do the bending moment and we do the shear force. These two lines is actually represent cross section. Okay. Now, if you focus on my hand a little bit, if this line is one cross section, this line is one cross section. Notice that when we turn it, when we twist it, if it's not connecting, it's just touching, what happens is the cross section will rotate this way, right? Notice the way the cross section moving is actually sliding on one another. Okay, the reason I have to emphasize is that if the cross section move in and out, it is axial stress, axial strain. If it sliding in shear, sliding that way, shear force sliding that way, when it slide, it is shear force, shear stress and shear strain. This one here is also sliding, although in the circle it's still sliding. Therefore, it is shear stress, shear strain. In other words, it means that torsion causes shear stress and shear strain. There we are, which I will summarize here. Okay, what we look at a member subject to pure torsion. Okay, then we discuss torsion cause the shear stress. Okay, if we talk about the shear stress and shear strain, then that is formulation. The shear stress is equal to the shear modulus times the shear strain. As long as it stay in the elastic region. Okay, now let's look at, we're going to simulate the physical phenomenon, right? This is the just to make calculation simpler, okay, we'll focus on circular cross section. Okay, notice this is not really a rubber, this is kind of like a tube. Okay, and we twist it, Tx minus Tx, so it's in equilibrium. Okay, there we are. Now if we look at the front view, okay, that is the front view, and then the other one on the right hand side is the cross section area. On the cross section area, I also did indicate where the centroid is. Of course, is the center of the circle. Okay, and of course the line we draw. In this case, what we do is I draw another line from the cross section, continue onto the front view. Okay, now if I twist it according to the two torsions, the minus Tx and plus Tx. T is torsion, X is meaning it's going about x-axis. Okay. Now, if I rotate it, then the red line turn into the blue line, meaning it rotates. Of course, on the side view, because it moves, you can imagine that the red line from being horizontal, twisting upwards. If we twist it that way. Now, just to be precise, okay, that is the angle we call gamma. That is the angle we define the shear strain. I emphasize myself, this gamma is shear strains. Okay, the angle you see on the cross section is in fact another one. We use the symbol phi. This one is called angle of twist, meaning how much degree or how much radian, depend on the unit, it has been twisted. Now, notice one thing though, on one cross section, gamma is constant. Not gamma, sorry. The angle twist phi is constant. Okay, look at that. Okay, no matter where you measure, from that point or that point is still the same phi, the same angle of twist. Gamma also throughout the whole length seem to be, or at least in this case, seem to be constant if there is only one torsion. However, if we look at a smaller, okay. Now, if we look at the cut section there, okay, meaning rather than looking at the end of the cross section at the end, what I do is I will cut maybe somewhere in the middle, okay, and then we have that. Now, if I look at the cross section area here, meaning I look into here, notice that even though gamma is a constant, our phi, the angle to which is no longer the same. Meaning, even within one pair of torsion, the angle of twist will change according to x. Okay, notice the total length angle of twist is big. If it only somewhere smaller, shorter, okay, then the angle of twist is smaller. Therefore, as I indicate here, the angle of twist phi is in fact a function of x. Now, to make it a little bit more complex, then we look back at the same pair, the pair and the end. Last time, what we do, we cut throughout the length, but apparently we can have another problem. If we look at a small radius of the cross section, this is total radius, right? We look at gamma, the shear strain, with the total at the end of at the what we call total radius of the cross section. What happens if we look in a smaller radius? Maybe we cut off here, like we peel off oranges, right? Then we will keep only the core inside. We look at the core inside here. We will take this part away, okay, and throw it out. Then if I draw that one, just that, we will see that. Notice that the angle here, because it's from still the end, meaning it's the same angle phi, the same angle of twist as that one there. However, when we relate back to the front view, then we have this picture. Notice that gamma is smaller. Why? Because this gap here is smaller than that gap, but the length is still the total length. Okay, so in other words, it means that the shear strain, although constant with one pair of torsion, I have to emphasize here, one pair of torsion, it's constant from the beginning to the end. However, it's a function of the radius of the cross section. Therefore, that gamma is gamma as a function of radius, whereas the outer rim, from the outer edge, gamma is one value, and probably the maximum, no, not probably, and is the maximum gamma. Okay, angle of twist is the same. Angle of twist is changing according to the x, the length, and at the end, that is the highest angle of twist. Now, so when we go on to formulate, then we have to understand that there is changing in these two angles with respect to different features. One pair of torsion within the same material, nothing changed. Then shear strain gamma is a function of radius on the cross section. Angle of twist phi is a function of distance on the x direction, of course. Of course, as I indicate, that one therefore is called gamma max, the highest gamma at the edge, at the outer edge. Now, if we want to relate these two, then let's say the total length from this point to this point is L. Okay? Then gamma max will be phi times the radius, the total radius, which in this case I call R, phi times R, that gap, meaning that distance, right? And then divided by total length. Okay? Confused? Let me try again. Gamma max is out from the outer rim, meaning gamma max is that picture, calculate from that picture. Gamma, if the angle is small enough, tan of the angle is equal to tangent of the angle is equal to the angle itself. Therefore, gamma max will be that side from that red line to that blue line, divided by total length here, which we indicate as capital L. Now, how do we calculate that gap? That gap, we can use that picture to help. Since that distance from red to blue is the same distance from that red to that blue, right? We're relating it all the time. Therefore, that can be calculated using the internal angle times the radius. In this case, it's phi times R. Therefore, that one is also phi times R. There, phi R over L. Right? Now, if we look at the smaller picture, the same argument, that gamma which is a function of R, okay, equal to that side divided by total length, and that side, that total length is still L, and that side is equal to that angle, which we call phi here, the same angle here, times the lowercase r, because in this time radius is only little case r, and then gamma can be calculated that way. In that case, we can find the ratio of gamma max and gamma by, of course, comparing them or dividing them, right? Comparing them, then we have that equation similar to the similar triangle, which is one side gamma over r equal to gamma max over r max, or capital R in this case. So we have the relationship that we can work on between gamma and radius. And of course, if we want to link it back to phi, to angle to width, then we have these two formulations that we can use. Now let's move on. And we summarize it a little bit. If a member is subjected to a pure torsion, then what we have is, it is shear stress and of course shear strain. That equation, and then we have find out that angle to width varies with the member length, meaning position of the length. Okay, meaning the longer you move, the longer you look at, the angle to width become bigger, and the shear strain gamma is vary with the radius from the centroid. Meaning you move away further from the centroid, gamma become bigger. And as we see, it's a linear relationship. Now let's look at the formulation. Okay, we look at the two formulations altogether. First, we will look at how we formulate the shear stress caused by the torsion. Then, of course, we look at the deformation of the torsion by the torsion. We are not looking purely at gamma though. We can look at the angle to width, meaning the change in the angle at different cross sections. Okay, go on. Let's look at the shear stress first. There. Well, we're going to look at a cross section, any cross section at all, we call A. Okay, with the radius, the total radius is capital R. This cross section is subject to torsion at the amount of T. Okay, we surely can calculate by now what that T is if we give the problem. So that T is not a problem, we will be able to calculate it. Okay, then we should look at a small area, dA. Now this small area, because we know that the change of the strain is with the radius, right? Remember, gamma, the shear strain varies with radius, meaning the stress which relating directly to the strain must be vary with the radius from the centroid as well. Therefore, the measurement this time will be measured as a radius from the centroid. Sorry. So we indicate dA, and of course we said that it is lying on a radius that we call little case r. It could be anywhere on that dotted circle. Okay, as long as it has the same radius from the centroid. Now, of course, on that area is subjected to shear stress, which you usually use the symbol tau. We keep the symbol tau for now. So that tau is acting on that dA. Okay, so the total force. Therefore, let's look at relationship first. We have gamma over R equal to gamma max over capital R. Okay. However, gamma is equal to tau over, is equal to shear stress over G, the shear modulus. Okay, but G is the same, right? Because it's the same material, so we can translate that gamma relationship into tau relationship. Okay, the shear stress relationship, and of course we move the signs a bit, we end up with this kind of form. Okay. Now, because we're going to talk about the shear stress for now, because then we have to turn it into forces, and then from force take into moment and then relate to that torsion. Okay, if we have a small if that force tau in that small dA, if that small force caused by shear stress in a small dA, then we can actually calculate the torsion from that small force. Let that torsion called dt, small torsion called dt, and then that caused by the stress inside dA. Firstly, we look at the force first. The force inside that small dA is equal to, of course, the stress times the area itself, therefore tau dA. That is just a force. Now, if we want to find out the moment, torsion is a moment, right? Therefore, it must time the arm. What arm? That arm must be 90 degrees to the rotation center, right? Now, this is rotation center because that tau is along the line of the circumferences. So if we draw a line from the center of the circle to the circumferences, it's already 90 degrees. Therefore, the 90-degree distance is the radius itself. Therefore, that term is the force times 90 distance. It becomes moment around x-axis in this case. So that is expression for the small torsion caused by the stress inside the small area. And of course, then, if we can change that tau, that small stress, because we're going to integrate it. That's my reason. Because we're going to integrate it, we know that the shear stress varies with radius. When we move the A around, then radius change, meaning tau change. Okay? R also the same I just said. Therefore, R and tau are variable inside integration total area, whereas tau max and capital R only indicate what happened at the outer surface. It's not changing with the integration of area. So what we want to do is reduce the variable. In this case, they will reduce the tau. They change this shear stress into that form. Okay, there. And hence, they can rearrange it as such. And once we put in the integration, these two terms are constant. Therefore, they can come out of the integration. Okay, we just clear off the area and then move that upwards and then put in the integration. Okay, once we put in the integration, as I explained before, then these two terms are constant, come out of the integration, and then we have this term left. That one we discussed in static already. That one is the polar area moment of inertia, J. Okay, and therefore we can calculate, change that form. Then we change around to actually find out what the stress is, and then we end up with the final equation for the shear stress caused by torsion. Move on further to calculate the angle of twist. Okay, that's the picture we discussed before when we peel off the outer edge of the tube, the outer edge of the cylindrical cylinder. Okay, and of course we have gamma. That gamma is not a gamma max, it's gamma that is already varied with the radius. Okay, now if we look at a small change in the small dx, okay, and try to link it back. Okay, now if we look at that small cut that we just looked at, then we have the two lines, the red line and the blue line. Okay, because it's cut in the middle of the beam, that blue line and red line doesn't meet at the beginning. It already have a gap. Okay, have a look again just to make sure. Okay, look there. There's a gap there and a gap there. Smaller gap, bigger gap. Okay, which we just represent there. Smaller gap, bigger gap. Okay. Then, if we want to see the change, notice that if I draw a dotted line, the dotted red line parallel to that red line, that angle is still the angle of gamma, the same gamma we looked at before. Okay. Now if we project it to the cross-section area on the left-hand side and cross-section area on the right-hand side. Okay. Of course, on the left-hand side view, that one, left-hand side view, we have phi to begin with before we move to the x. And of course, from here, it's no longer phi, it's no longer the same phi, it's no longer the same angle to twist because it has changed, it has bigger. It become bigger, you can see. Okay. Now, what we want to see is how much bigger it become for this small section. Therefore, if I draw that phi is project from here to here and then draw it through the centroid. That phi will be the same as that phi and the same as that phi and that phi. Okay, the same angle to twist. And that small from that dotted red to the blue is the change in the cross section. The same with that one, which I will call it d phi. Okay, once we don't forget that that d phi and that d phi is the same d phi. Now we're going to link gamma and d phi into each other. How do we link it? By this side, this side and this side. Okay. Now, if I call that A and B, that is A, that is B. We can calculate the length AB from the two pictures, that picture and that picture, of course. We agree? Okay. There we are. That is also A and B. That AB from that picture, as I indicate, then of course equal to gamma times that one, dx. Don't forget, this is small gamma. We're talking about again in a small displacement concept. I repeat myself, small displacement concept. If it's small displacement, gamma is small as well. If gamma is small, then tangent of angle is equal to the angle itself. Just the words of saying this, it means that on this left-hand side, the unit we are using here is not degrees. The angle we are using here is radian. Okay? But then it calculates as gamma dx. What about that then? That AB. That AB, this is a circle, right? On this right-hand side view is a circle. Then the arc length of the circle is equal to the internal angle times the radius. Again, once I said it, once I state this, d phi, gamma we already discussed is radian. D phi of phi in the end is also radian because it's equal to the arc length divided by the radius. Okay, and here we are. That AB is also equal to the radius. In this case, not the capital radius, not the total, the smaller one, times the change in the angle twist, which we call d phi. Of course, these two are the same A's and the same B's. Therefore, the two sides are equal. And then we have relationship between gamma and the shear strain, and phi, the angle of twist. From that, we move on and work on that equation. Then on the left-hand side here at the moment is the one that we derived from the last page. Then if we change a little bit to have d phi on one side, then move the other thing onto the right-hand side, we have the right-hand side form. And of course, when I set this up, you can guess what has happened. We're going to integrate it. Notice that this is, well, I haven't actually set it up yet, but I don't think it's purely accident. But in the end, d phi on one side, dx on the other side. When you integrate d phi, then it will be with respect to the x. As we discussed, the angle to twist change with x. So this seems appropriate. Then if we integrate it throughout the, we change it a little bit first. Okay. Now gamma is good. The only problem we have is that we have no linkage between gamma, the shear strain, and what we know from the static side, from the mechanic side, this is torsion. So, but we have relation between the shear stress and torsion, and we also have relationship between the shear strain to the shear stress. So we will change it to the shear strain to the shear stress, and then change it again or relate it again to the torsion. So with the left hand side is the elastic region for the shear, G is the shear modulus, work the same way as the Young modulus in elastic, in axial. Okay, then we have changed it to this form. Then of course, as I indicate, we can change tau into the torsion itself, and then we have the final form. Okay, and if T is a constant, J is a constant, J is the polar area moment of inertia, is a constant, and shear modulus, well, one material is constant, then this integration will be like so. Okay, and then we can calculate the change in the angle. This is the summation of the change in the angle from A to B. So the equation is similar to the axial deformation, though, I have to say. Well, I leave you work out that similarity. But in the end, these are the equations we focus on. Let's look at the formulation. It has been a long journey today. Okay, let's look at what we have done. Okay, we have expression for tau, or the shear stress. This is the shear stress caused by the torsion. Okay, and we know the definition of J, the polar area moment of inertia. Okay, then we also work out the equation for the angle of twist. And what happens if T, J, and G are constant? If all of them are constant, then this is the expression. So mainly for this topic, that one is for these two are for the stresses, and these two are for the angle twist deformation, that is. Okay, then let's see how it actually works in action. Okay, first, because we haven't done much on J, or the polar area moment of inertia, so we'll do it here. Okay, let's look at a circle. This is a circle. The total radius is capital R. Okay, what we want to find out is what is the value, or how we calculate the polar area moment, of inertia for this circle. Okay, now if we look at the expression, okay, it is R squared dA, right? So when we look at dA, we need the dA that is having the dA that have the same radius all the time. In this case, of course, we look at a ring, right there. That's the ring. The thickness of the ring is dr, and the position of that ring, or every single point of that ring, is defined by the lowercase r. And dA is the total area inside that ring. Okay, then that is the expression as I indicated before. Now that area dA then is equal to the length of the circumferences times the thickness. The length of the circumferences, of course, is 2 pi times r there, because r is the small radius r, and of course the thickness is dr. The total length of the circumferences times the thickness is the total area. Substitute into the equation of the integration. There we are. Simple integration done by one step. And of course, that is the n. Then that is the J for the circular area. Now, once we know how to find J, which is pi r to the 4th over 2, okay, then we will actually look at how we calculate the shear stress and the angle twist. That this beam is a circle cross section throughout the same circles, and it's the same material. Okay, the shear modulus was given here, is given here. The question asks the shear stress at point 3 here. On the cross section at point 3, on this cross section on point 3, there are 2 points that they want to know. point A and point B. They want to know the shear stresses on these 2 points. And also they want to find out what is the total angle twist at point 4 at the end there. Okay, before we start, look at the equation a little bit. Now, by my consideration, I think we can subsidize, we can divide it into section of the length where the torsion is constant, J constant and G constant. Therefore, I will be looking at that formulation for the angle twist. And then that one is for the shear stress that we need to find out, and of course J of a circle we discussed before is that form. Now, let's look at torsion first. This is the total free body diagram. The T1, the rate T1 is the unknown, which is because point 1 is stuck to the fixed support. Look at the equilibrium. Okay, one unknown. Okay, one unknown, one moment equation would be enough. Therefore, T1 can be calculated as 60 kilonewton meters. Once if we calculate T1, then of course we will look at the internal torsion. Okay, between 1 and 2 will be then of course cutting between 1 and 2. The torsion then we call T12. Okay, simple calculation. There we are. Now between 2 and 4, apparently 3, although indicate between 2 and 4, it doesn't have any external forces adding in, or in this case external moment. Therefore 2 to 4 has only one value of torsion. Therefore we ignore the fact that we have point 3 around there for now. Okay, so we draw from point 1, point 2, and then of course between 2 and 3, or 2 between 2 and 4 the same. And then of course we can calculate the value of torsion there. So we have our torsion between 1 and 2 and between 2 and 4, 60 and 40. Okay, although on a different directions, but we will see how to cope with it. Now, let's look at the J then. Although we look at the 2 points on the cross-section area, however, J is similar to I, is calculated from the total cross-section area. Okay, it doesn't matter which point you're looking at. J, when we prove it, it integrates total area all the time. Therefore, we just calculate it as the total cross-section area, meaning using 3 centimeters. Okay, we already calculate and we know that torsion at point 3 is equal to 40 kilonewton meters. Okay, then we substitute for point A, which have R, okay, TR over J, T 40, J, as we calculate here, that one R from here to here is 3 centimeters. Substitute it, we have the answer. For point B, then R is reduced to only 2. Notice J, still the same value of J, because although we look at the point where it's 2 centimeters, J is calculating from the total area. It isn't affected from the point you're looking at. As long as it's on the same cross-section area, J is the same. Okay, so we have find out the 2 shear stress we are asked to find. Okay, next the angle twist. Because we have 2 sections, 1 and 2 is one value of torsion, 2 and 4 is another value of torsion. Then of course similar to what we do with the axial forces, we have to look at 2 different sections separately, then combine the effect. Okay, this is the total picture. That is the equation for phi. Now between 1 and 2 we calculate already 60, right? And it's a positive x. Therefore when we calculate between 1 and 2, then phi is using 60, and of course torsion is positive x, the rotation also positive x. And then 2, 4, the torsion is 40, negative x, calculating it. Therefore the angle twist going in the negative x direction. How do we calculate at point 4 then? Similar to what we do with the axial forces, axial deformation, we go where it's fixed first, and then these are calculated relatively to the beginning to the end, from the beginning to the end. In this case, apparently point A is fixed, point 1 is fixed. Therefore, the angle to width of point 2 is equal to angle to width at point A plus angle to width between 1 and 2. Fixed support, therefore phi 1 is 0 plus phi 1 2, then equal to just that. And of course, from 4, then we combine the two effects. Phi 2 start and then plus what changed between 2 and 4. Okay, phi 2, there we are, phi 2 4 minus though, so end up minus into the minus direction, and that is the last answer we need. Okay, so let's summarize all the answers we have. We found the shear stress on the 2 points A and B, which is on the cross section at point 3, and then we also find the angle to width of point 4, and that concludes our answers. Let's look at what we have done today. We find out that the torsion caused the shear stress, and of course it has to come together, shear strain. Then we find out the angle to width, which is the rotation of a cross section, varies along the member length. Okay, whereas the shear stress and shear strain vary with the radius of on the cross section. And then we find out the formulation for the shear stress. Then we find out that we have to work out on another type of area moment of inertia. This one is polar, okay, which we use J, not I. And we also found the expression to calculate the polar area moment of inertia for circle. Okay. And then of course, we actually also find the expression to calculate the angle to width. And I think that this concludes lesson for today. Thank you very much, and see you next time.